call me professor. And then they figure it out. But sometimes they act like, oh, that's just a nickname, but most of them know.
Street ball nickname.
Dr. Ball.
Yeah, there was one guy who actually came a week or two ago, and he didn't play in a while. So I just thought they called you professor. So you're teaching physics? He's like, yeah. And I guess he works at Devon or something. And now he's trying to take my class. Thinks that I'll be easy on him or something, but he doesn't really know.
Get up all in his face.
Okay, so let's look at this expansion problem here where you've got brass and aluminum, a couple of strips here of metal. And these actually have some area to them, but all we're going to care about is the expansion in just the one direction to fill up this gap. So basically you have these two pieces of metal here and a small gap in between them, and you want to know what temperature do you need to make these fill up the gap. What temperature do you need to raise the room to, or whatever these are in, to fill that gap in between these two pieces here. So let's say here we've got these two pieces, one's a meter, one's a couple of meters. We've got brass and aluminum over here. We have a couple of meters on this side. And then 1 meter over there on that one. At 28 degrees Celsius, so in this situation right now, the gap between the rods is 1.3 times 10 minus 3. So this distance right here is 1.3 times 10 to the minus 3. Let's just call that x for a variable. Okay. We're going to raise the temperature so that this gap is now closed. So what's happening there when we raise the temperature? These bolts expand to fill up that gap there. Okay. So, well, first thing we could do is probably look up your constants. You know, you're doing expansion problems. If something's expanding due to a temperature change, then you just know right away you're going to be using your delta L is equal to L naught alpha delta T. That's what's describing the expansion. So we can look up our alphas. Let's say we've got an alpha B for brass, alpha A for aluminum. What are these numbers for the alpha for brass? Times 10 to the negative 6. What about this one over here? Do those have units? You're not going to see it right there with all the numbers in the table, but on top it tells you these are all in degrees Celsius to the minus 1. So make sure you include that when you write these down and use that when you're solving problems. This temperature here is the temperature right now when the gap here is 1.3 times 10 to the minus 3. This was in meters, right? This number here?
Yeah.
Okay. This is our initial temperature then also for the 28 degrees. Okay. I'm just going to kind of list this out now with the alphas, the L's, the T's. Let's just write a list here of the L naught. And let's call this L naught B for the brass. So that's going to be our 2 meters. We have an L B, which is unknown. We have T naught, which is our 28. Then we have a T final, which is unknown. I'll just erase this one now since I've got it here in this full list. Do I need B's on these T's right here? Why not?
It's the same picture.
Same for both, so we don't need to worry about that. We're going to have an L naught A over here, which is a meter. We're going to have an L A. We have T naught of 28 again, and we have T. Okay, that's just all the information that's going to go into those equations there. How can we write an expression that says we're going to close that gap? What could I write down that would say the gap is going to be closed as an algebraic expression here. We need something to close the gap.
Should it be LOB plus LOA is equal to 3 plus 1.3 times 10 to the negative 3?
So this plus this is equal to this total length right here? Yeah, you could say that this whole thing should add up to that distance there. What's another way we could write that? That might be a little bit easier when we're going to go to our equation. That's not wrong, that could work, but there's going to be actually a shorter way, or a way that's going to be more convenient for plugging into the equation. Think about just the gap instead of the whole thing. Think about just this region right here. How can I fill up that region? Well, we're doing it by expanding these two, right? See if you can think about a statement that I could write.
So LB plus LA equals delta L?
Not the whole LB and the whole LA, because the whole LB and the whole LA would be equal to the total distance here. What about just that part right there?
Would be LB minus LA?
LB minus LA at the end would be equal to that. Let's get it in terms of something else. Anybody see another way to write that? What haven't we tried yet? We've been working with initial lengths, final lengths. What else is there? Temperatures in there also. I hadn't written it down here, but what about the delta L?
It would just be delta L is equal to 1.3 times 10 to the negative 3.
Well, but we have two things expanding here. So think about this. When you expand, heat these up and they expand, this is going to come out to a point over here. Right, and I'll put this other one in a different color. And then this one will expand and come out maybe over here. And they're going to be different lengths because they're different materials. Okay. What would represent these two little lengths right here that I have in blue and green there? The two different delta L's. This would be delta L for A. And this would be the delta L for B. In terms of my delta L's, how are those related to the gap?
If you add those together, they equal delta L.
So delta LA plus delta LB is equal to, let's just say, the x for now. That's probably going to be the most convenient form to keep it in, especially since we start with this equation right here. I don't want to say everything because I might have heard something wrong, but almost everything you guys were telling me with all the equations you were saying for the L's was right. But if I go back and check the video, there might be something wrong in there. So I'm not going to say everything. But most of what you guys were saying for those relations, that was good. And I was just trying to get us to here because that's going to be more useful. Especially because we have this form right here. And it also just takes into account just this distance right here, which probably makes it easier when we're doing the equation. So, what is delta LA? How could I write the equation for delta LA? What would that be equal to? If I was going to solve for what that was, how would I find it? Just this right here. So everything expands based on this equation right here. We have two different things that are expanding at the same time, but we just found the relationship that connects those two to each other. Let's just put this in as L naught A, alpha A, delta T. This is L naught B, alpha B, delta T. That's all equal to X. Everybody see that? Okay. Well, we know the initial lengths. We know the alphas. We don't know delta T, but we know X. So we can solve for delta T. Let's factor that out. Like that. Because there's a delta T common in both of these terms. We'll just divide out that parentheses there. Get delta T is equal to X over L naught A, alpha A, plus L naught B, alpha B. Okay. And we have all the numbers in there now for the X, the L's, and the alphas. What are we solving for here? The the temperature, so not the change in temperature, but the temperature here would be T minus T naught, so I could say T is equal to basically this plus the initial. You could have solved for that number separately, and then just added that on to the original 28 that we had, or to show it here in the equation, it would just be, I'll just put the number in right now, the 1.3 times 10 to the minus 3 divided by the L naught A, which is a meter, the alpha A, 24 times 10 to the minus 6, and that's in degrees Celsius, minus 1. And then we have our 2 meters for the brass, and the 19 times 10 to the minus 6. And then I'm going to add the initial temperature of 28 degrees Celsius, because this delta T here was just T minus T naught, and I just added over the T naught to the right hand side. So we can plug all those in and get a temperature of 49 degrees Celsius. Make sense there? The key on these is if you have more than one thing expanding, you have to find the connection between the two. There was some relationship here, in this case we wanted to close that gap, so we had to write this out, or something that relates this here being closed. And the other statement that Ben was talking about at the beginning that said that the final length of B plus the final length of A should be equal to this whole thing, 3 plus that right there, that would work also, but that would have meant we had to expand these out, and there'd be a lot more terms in the equation there, and so it'd be a little bit longer. But that still would work. Anything like that, though, is something that you're going to have to do if you have more than one thing expanding at the same time like this. Okay. And then just know that this equation, the deltas might have to be written out as final minus initial if you're solving for anything inside of it. Okay. Individually, each one is just this little piece right here. Those aren't too hard to work with. Everybody good with that?
Where did that plus 28 come from? Is it
This was adding over the initial T, and so the initial temperature was 28, and so this was delta T,
I see.
where that is T minus T naught,
Mhm.
and then just added it on to the 28.